science student you are, you still get high quality instruction because you learn from Mr. McKellips. And that makes this a little easier to teach. That said, I'm going to focus on the calculus of this. I'm going to have to ask you to check all those memorized equations at the door. You're going to develop the equations via calculus. Those equations don't just pop out of nowhere. They came from calculus. That is the goal of the day, but let's start here. I could not get the phone thing to work. I wanted to do some kind of cool activity where you use stop motion on your phone. I'm technologically enough. So it didn't happen. Instead, I posted this picture in here. This serves two purposes. First of all, it's the old, doesn't matter the mass of the object, they fall at the same rate. Yeah? Okay, feather in the bowling ball. Okay, this is the way my physics teacher taught. Neglecting air resistance, of course. So you can see that these balls, both the big and the small, after so many seconds, fall exactly the same amount. Now, the question, though, is what about gravity? We need, in order to do any of these problems, we need to know what gravity is. Now, I know you have memorized the acceleration constants for gravity, but let's just real quick walk back in history about how they were found. This would be easier done over a huge span, but this is dropped over a small little centimeter component here. I took every other ball here. I didn't want to spend all day just doing ball dropping stuff. I want to get to the calculus, but I'm doing every other one. Now, here I'm going to call this height 0. So at time 0, height is 0. Now, skip the bottom of the first ball and go to the bottom of the second ball. And let's take a stab at the height. Now, over here, it's practically impossible to read, but those are centimeters. That's 10 centimeters is that first white mark here. I want you to then estimate where the bottom of the second ball is, but also put it in meters. So what do you think, feeling here? Okay, it looks like about 6, 7 meters. Yeah? So let's go with, how many meters would that be? 0.06 meters. All right? Now, skip ball 3 and then go to ball 4. That's between 10 and 20. Just take an estimate. What do you think? 15. Okay, I'm down. 0.15. 15 centimeters, so about 0.15 meters. Skip a ball, skip this one, go to this guy. What are you thinking there? 0.29? Is that what you said? Okay, I agree. Skip a ball, go to the next. What are you thinking there? It's between 40 and 50. What do you think?
46.
46, okay, sounds good. Skip a ball, go to the next one after that. Oops, I missed, but you get the idea. So what are we at there? That's 50, 60. That's between 60 and 70.
69.
68, 69, okay. We'll go 68. Skip this one, go with this guy. Where are we at there? I've lost track. Now 70, 80, 90. That's between 90 and 100. 93. Okay, I agree. Sounds about right. And skip one, go to this one. That's between 100, 110, 120, and 130. What do you think? 1.25? Or 2.4? What do you think? Okay. Okay, cool. Now, the next thing, if I want to establish, so this is, we'll get to the calculus in a second, but I am taking the 10 minutes to do this because this is all huge not basic math. It's math modeling, all right? This is the type of math you might actually use on your job sometime. Taking data and trying to make sense of it. That's modeling. It's easier to make a model, and when I say a model, I mean an equation that models the data. It's easier to make a model from a graph than it is from a table. Tables are kind of hard to look at and say, oh yeah, that's sinusoidal, or oh, that's linear. Well, actually, linear is pretty easy to see at a table, but you get the idea. And so instead, let's graph this. Would you draw me a fourth quadrant kind of graph here? Actually, would you put the y-axis right under the 0 of the table, because that's going to be my origin. You cool? I'm going to show these time intervals 0.042. These pictures were taken every 0.4 of a second, okay, with the stop motion camera. So those time intervals of every second ball, those are 0.4 of a second, 0.4 of a second, 400ths of a second, excuse me, not 0.4 of a second, 400ths of a second, 400ths of a second. So each of these is just going to represent the time in the table. You follow? Okay? Rather than write those all over again. The y's are the heights. They're really, I wrote it all here because these are all negative. If this is height 0, aren't these really, I guess they have been all negative. I know in physics you'd probably say, oh, it depends on how you define your axis, but in that, when we say down, down is negative, period. There's no defining your axis, okay? That was not my impression of Mr. McCullough's voice. If I was trying to do Mr. McCullough. Okay, I'd give anything for his manly. You know what I'm saying? He's got like a voice. All right, we need to go to about 1.2-ish. So let's go with every negative 0.2 or so. So we don't. I guess we could do every 10th, but I don't want my graph to get too busy. Or so. You follow me? Now, plot each of those locations over time. So at time 0, the height in meters was 0. At time 0.042 seconds, the height was negative 0.06. Now that's in there, not much there. Negative 0.15 is a little closer to the negative 0.2 mark. Negative 0.29 is the third x value, a fourth x value, I guess. But that's, it's pretty close to between 0.2 and 0.4, you follow? Mm-hmm. And 0.46 is here-ish. 0.68 is pretty close to between 0.6 and 0.8. 0.93 there. And 1.24 is down here. Okay. So far, so good? Are you with me? Okay. All right. Now we have some algebra skills that we could use to write an equation of this. We could pick 3 points and try and write an equation through this, but the calculator does that really well. The calculator is programmed to do a calculation that minimizes the distance from the equation or the graph to those points. That's regression. So when you use a calculator to fit a curve to data, that's regression. We're going to do quadratic regression because we know the shape of this should be quadratic. So if you get out your calculator, let's practice this. This is, again, a skill you need in stat and a lot of, anytime you do research, you'll do regression. Okay, so this is what I'd like you to do. Rather than do your scratch pad, go to Home and open a new document. And we're going to add a list and spreadsheet, okay? Are you with me? Should I do that again? Go Home, new document, list and spreadsheet. Here, in A, you're going to do time. Or M. Not really M. T. T. Oh, golly gee. What the heck? Am I? T. Would you put in the times 0.042? Oh, yeah, we now start at 0 come down. Sorry, that's me. 0, yeah, 0.04. No. 0.126. Then go to the next column and put height in. Yes. I'd have to walk you through the regression on that. It would take a while. I can get you the write-up of the instructions if I remember. Do you have that data in? Will you put the height in column 2, please? Do put the negative in, please. By the time I hit 80, I might have this data in. Okay. Height. Oops. Okay, so 0, negative 0.06. 6, negative 0.15, negative 0.29, negative 0.46, negative 0.66, negative 0.93. Okay. Yay. All right. So it really doesn't matter where you go, but go over here to the side where you're going to have the calculator do the regression. Right now, when I say do the regression, it's going to find an equation of a parabola that gets as close to the data points as possible. To do that, you go to menu. Again, you should be in a cell over here outside of your table, or to the right of your table. Go to statistics and stat calculations, and you're going to do quadratic regression. The reason is that data is not linear, it looks like quadratic, so that's what makes sense. The X list is T, the Y list is H. The rest of that stuff you can blow off and go straight to OK. Now, when it does that calculation, if you scroll up a little, it gives you the correlation coefficient. It's a really strong correlation coefficient if you went down to R. But that's because this is not kind of, people's feelings about stuff where it's a data cloud and it's all over the place. There's not really a trend at all, and you're a social scientist trying to pretend like you're a scientist, and it's not that. It's actual science, okay? So it's predictable, reliable, able to be regenerated. That's why the correlation coefficient is high. In social science, you shoot for a correlation coefficient of 0.6. It's whatever. Hey, don't get me started, okay? So anyway, these are what we need. A, B, and C, they're the constants in the calculation that we want. So negative 11, acceleration, the equation for height as a function of time is negative, what was it again? Negative 11.574 t squared. What else after that? Minus 0.789 t minus 0.0029. Okay. Now, that's obviously going to be a little off because we have measurement error. What should the height be when time is 0? 0. I mean, it's close. It's 200ths or 300ths. But, there's a little error here in the error of measurement. Okay? We were, after all, taking stabs at the heights, not actually nailing it. All right. Now, the idea of this is from this, we can do a little calculus to get acceleration due to gravity. What is the first derivative of height? What does it mean? What's the change in height over time? Let's change in position with time. Velocity, yes, okay. The velocity is negative 20, what do we got there? Negative 23.148 t minus 0.789. And what is the second derivative of height, or the first derivative of velocity? Acceleration, and that is, in this case, negative 40. Oh, this is t, sorry. Negative 23? Wow, we really failed this. God, this is terrible. We're not even close. When I did this by myself yesterday, got much closer. This is not. This is terrible. Okay, because what should we be getting? Negative 9.8. Well, that's a measurement error for you. So make sure you get actually in with more measurements and better. You could get much better precision if you dropped it from the Empire State Building instead of over a 100 centimeter or 1 meter distance. But it's all good. Acceleration due to gravity, get both. You'll get both problems in the homework. So you need to know that both negative 9.8 meters per second or negative 32 feet per second. Please read for units carefully in the problem so you know which one to use. Okay? Now, let's get to the actual problems I expect you to do. Let's get to the calculus. I'm not sure if that was actually worth it for such a terrible. All right. Anyway, this is the type of pretty typical problems I will expect you to be able to do. Calculus of physics. So a ball is thrown straight up, at least from a point 5 feet above the ground. The ball reaches a max height of 69 feet at time 2 seconds. Find the equations for velocity and height using calculus. When I go to grade these, and I will be grading for your work, not just the answer, I will be looking to see, is this kid just thinking he's in physics class and giving me position is, or you don't even call it h, negative whatever, 1/2 g squared plus v initial. That's not calculus. That's physics memorized equation. Calculus is where that comes from. So this is what I will expect you to show. I know, or you would start by saying, I know that the velocity is the antiderivative of acceleration. And so your first step should either be saying v is the antiderivative of a, or the antiderivative of negative 32. I don't care, but you should be showing that velocity comes from anti-differentiating acceleration. It's the antiderivative of acceleration. Then take the antiderivative. The antiderivative is negative 32t plus a constant. Now, because we're going to actually integrate it twice, one for the velocity, one for the height, I'm going to call that C1 because I expect 2 constants over the course of this problem. You with me? Now we're going to use an initial condition to find C1. The only way we can find that C1 is if I have a V and a T case to put in. What do I have? I know that, max height of 69 feet at 2 seconds. Now I know that doesn't imply, or doesn't clearly state a velocity, but it's implied. If it reaches a max height, if the height is 69 feet at 2 seconds, what's the velocity then? 0. We're talking velocity going from positive to negative. So it's kind of implied within that the velocity is 0 at time 2 seconds. So what is the constant of integration? 64, negative 60. It would be 60/40, yeah? Okay, velocity is negative 32t plus 64, therefore, and my velocity equation is complete. Now I've found the first part. It says find equations for velocity, done, and height. Now, the next part is another sequence of the same kind of work. Calculus, antiderivative, find the constant. Height is the antiderivative of velocity, eh? So it's the antiderivative of negative 32t plus 64. So I didn't give you a lot of room to work there. What's the antiderivative of negative 32t? Negative 16t squared plus 64t plus c2, a new constant. In order to find C2, I need a T and an H to put in. Do I have a T and an H to put in? What do I put in? 69 here for a time of 2, so I get negative 16. 69 equals negative 16 times 4 plus 64 times 2 plus C2. What is that? Negative 69 equals negative 64 plus 128. Follow me? 69 equals 64 plus C2, so C2 is 5. Therefore, my height equation in its entirety, with the constant in, is plus 5. Did I give that initial height earlier? Oh, what the heck? Why didn't I use that? That was dumb. Oh well. Okay, well there you go. Don't you agree that makes sense, that at time 0 height is 5? So that's logical. All right, just so we're clear, I do not want to see anything like this. This is very common, especially the BC students. They're always doing this stuff. Integrating integrating acceleration is negative 9.8 t plus v naught. That's true for these problems. It's not true for every motion problem. And so I would rather you just do something that works all the time, which is calculus, and to say that velocity is always the antiderivative plus a constant of integration. Okay? In some cases, that constant of integration means the initial velocity, but in some cases it does not. So let's just go with what always works, and that's the constant. Okay? All right. Same kind of problems. You guys probably don't watch Road Runner anymore, but I was a big fan of Road Runner growing up. Wile E. Coyote falls from a cliff. This also, I watched a Wile E. Coyote and timed how long it took him to, finally hit the ground. Took him 7 seconds to hit the ground. How high is the cliff in meters, given that it takes him 7 seconds to hit the ground? Show the process. I want you to start from acceleration due to gravity. Acceleration due to gravity, in this case, do I use negative 32 or negative 9.8? Negative 9.8. Why? Because it's in meters. Okay, so we use the acceleration constant for meters, which is negative 9.8. Now we go to velocity. I think you'll agree that if we want how high, we need the height equation. But I can't get the height equation until I have the velocity equation. So I'm going to find the velocity first, then the height. How do I get velocity? Antiderivative of acceleration, which is negative 9.8 t plus a constant. Now some of these require you to kind of use your noodle here. You got to think through here. What velocity at time do they give you? The key word there is falls. So think of it like he doesn't. So if he jumps up from the cliff, he will have an initial velocity that's positive, yeah? If he dives down from the cliff, he'll have an initial velocity that's negative. But if he just steps off the cliff and just plummets, then his initial velocity is 0. Okay, so this falls implies that at time 0, his velocity is 0. Now, if you do that, then that tells you that that constant of integration, in this case, is nothing. Velocity is negative 9.8 t. In other words, velocity depends on gravity only, no other part of my movement. no Wile E. Coyote kind of initial velocity component. Yeah? All right, now we get to height. How do we find height by calculus? Integral of velocity. You don't need to show the integral of v and the integral of the equation. If you wanted to just write the integral of negative 9.8 t, that's fine. But what is the antiderivative of negative 9.8 t? Negative 4.9 t squared plus a new constant. To find that new constant, c2, how do we do it? Yeah, we really, yeah, 7 seconds, and the height is 0. I love it. Okay, so height is 0, negative 4.97, or times 7 squared. That implies that C2 is negative 4.9 times 7 times 7. I don't know what that is. 49 times 7, that's 240 negative, positive when I moved over, 240.1. Okay? So the height equation is negative 4.9 t squared plus 240.1. Now we can answer the question. How high is the cliff? 240.1. Why? Why is the constant the same as the initial height? Because at time equals 0, his height is, yeah, height equals is 240.1 at time 0. So the height of the cliff must have been 240.1. Cool? Okay. Try one on your own. See if this is. I want you to focus not so much on the answer, but showing the calculus. That's the part where you. I'm confused. Do you have a velocity to put in to find C1? No, actually C1 will kind of represent the initial velocity. C1 is really the start of the show. That's what I want. C1 is the initial velocity because it's what velocity would be when time of 0 goes in. So I guess I'm going to have to bypass that and go on to the height. Leave C1 as C1 for a second and go on to the height, okay? Go to integrate, it is a constant, so treat it like a constant. So your antiderivative should be C1t. If you understand where you're going, keep going. Go. But if you're hung up, where do we go now? We have two conditions here. When time equals 0, what's height? 2. And when time equals 4, what's height? I assume that means when it's hitting the ground, right? So at time 0, height's 2. At time 4, height's 0. The nice one to put in is the first one, because when you do that, these both 0 out, and that tells you C2 is 2, yeah? Then how do we find C1? Plug in. At time 4, the height is 0. So C1 is, sorry, let me zoom out for a second. Something ugly. You have that? What is it? 14.6. Anybody confirm that? 17.6?
It's 4.9 times 4. That would be. Yeah. So like, wouldn't it? Oh, I just did it in my head. Yeah, I did 19.1.
19.1?
19.1. Oh, I did minus 20. That's fine.
Okay, so we're 19.1, it sounds like we're getting agreement on? Okay, thank you. All right, so are we done? I guess if we put that into the velocity equation, negative 9.8 t plus 19.1, doesn't that mean that when time equals 0, the velocity needs to be 19.1? What are the units on that? Meters per second. That's the answer to our question. Follow? Okay, try the last one. Hello? Who that?
Here.
Hi, thanks. Yeah, he's here. Be careful with that falling. Falling needs to be handled with delicately. What does it mean? Negative. Velocity is negative, that's not positive. And obviously you get a huge error if you use positive too. So I guess I was just about to find the height, but I guess I don't need it. What's the initial velocity? 1 meter per second. At time 0, velocity is 1 meter per second. That's the question. I guess we didn't need it. You follow? Okay, cool. That's pretty much the deal. Question on the homework. Let's look at the backside first. Is this the top of the backside? Right, okay, cool. Let me give you the answers, then we'll hit questions. We're on time. Okay. For A, I have dy dx is 5 over x root 4x squared minus 25. Yeah, yeah? Okay. With process, obviously. Dy dx for B is negative 2 over 4x squared plus 1. Oui, oui? Oh, I don't hear a lot of wee-wees. Arc sine's derivative, just by recall, the more you write it, the more you remember it, is 1 over root 1 minus x squared. And arctangent is 4 over 1 plus x squared. Using those, then, did you do quotient rule here? Or did you put it to a negative exponent and use change?
I did a negative exponent and changed.
I did negative.
Okay, you could do it either way. If you did it as negative exponent and chain, then this would be your approach. You're saying, I have arctangent within the fraction kind of function, and you could do it that way. I did it by quotient rule, but our answers should be roughly the same. My answer by quotient rule was negative 2 times 6x minus 1 for the inside derivative over 1 plus 3x squared minus x all squared for the arctangent derivative, all of that over arctangent of 3x squared minus x squared. I'll give you a second to look at that because that takes a lot of looking over. Let me know if you disagree. For f, y prime or dy dx is first stays the same. The derivative of the second is 1 over root 1 minus that guy squared, but then times the derivative of the inside is times a negative 1. Plus second stays the same. Arc sine of 4 minus x times the derivative of the first is just 2. Okay. Equation on a tangent line. I use the point 0, and what is the arctangent of 0? 0. The slope comes from the derivative. The derivative of arctangent is 1 over 1 plus x squared at 0 is 1. Therefore, your equation is just straight up y equals x. F at 0.2 then is approximately the same as y at 0.2. And when x is 0.2, y is 0.2. So your estimate is 0.2. I probably need to give you guys more practice on tangent line estimations. It's a big deal with calculus. It's sure to be on the AP test. You need to practice it more. This, first of all, has stupidity in it. This x should be between negative 1 and 1, not pi over 2 and negative pi over 2. That's the range, not the domain. I'm dumb. Sorry. So the concave up and concave down, I think you'll agree, is about the second derivative. So did you start by taking the first derivative, which is 1 over root 1 minus x squared, or if you like, 1 minus x squared to the negative 1 half. And then the second derivative is negative 1 half, 1 minus x squared to the negative 3 halves times negative 2x. Cleaned up a little is positive because the negatives cancel, the 2's cancel. I get 2 over root 1 minus x squared cubed. If I break that 3 halves exponent into a root and then a cube. And then I did a sign test on that around zeros. This 0 is where it'll change sign. I think you'll agree, yeah?
Yeah.
So between, I get a negative and a positive for the sign of g double. So my conclusion is that g is concave down on negative 1 to 0, and g is concave up on 0 to 1. I don't know how much you remember the graph of arc sine, but it looks like this. And so that verifies what I know of the graph. Cool? This was for arc sine. For arctangent, not sine. Sorry, right? Arctangent, absolutely. My bad. You didn't have to show work for that. This required U sub. With U sub, I had 2/3 arc sine of 3x plus c. And this required U sub arctangent of log of x plus c. Cool? All right. These are the ones that you had to do that warm-up kind of work for. I have arc sine of x over 5 plus c here. 1/7 of arc sine of 2x over 7. Arctangent, what's my problem? Yeah, I did write arctangent this time. The other one I missed, but this one. Arctangent, thank you, yes. And this guy was 1/10 arctangent of 3x squared over 5 plus c. And I did not do the front replacement. Shoot. Let's see. real quick. Did you get a picture that looks something like this for rate out and this for rate in? Yes? No? Where did they, anybody know where they intersected? Time equal, not for Pete's sake, you're the worst. So 0.42 squared. Man, that's a freaking mess. So you would have to find the intersection by calculator. That's not going to be pretty. So I don't have the intersection point, but let's just call it A. You would have to find the intersection point. In this section here, R, which equals the rate out, is greater than I, which equals the rate in. So if more are going out than are coming in, then will the number of weasels be increasing or decreasing? More leaving than incoming, so it's decreasing here. At this point, the in rate and out point are exactly the same, so at that point, the rate, or the amount of people is not changing at all. And then afterward, the in rate is greater than the out rate, so then the number will increase. You follow? Okay, so I don't know where time equal 4 is, but I would, if I were you, I would compare R at 4, which is the rate out, and I at 4, which is the rate in. And based on which one has the greater rate, R at 4 is what, 10? And I at 4 is, what is it? 16. Is that a 2 or a 3?
2.
A 2, so 16.
It's a 3, sorry.
It's a 3?
That is a
So 64, 256, 2.56, or 25.6? 25.6? Okay, 25.6. What do I conclude? Is the number of weasels increasing or decreasing? Increasing. The number of weasels is increasing because I at 4 is greater than R at 4. And you have the evidence to back it up. All right. Last but not least, absolute min number of weasels. The absolute min occurs at n.
max.
You have max. Thank you. Absolute max occurs at endpoint or critical number, yeah? The endpoints are obvious, times 0 and 8 as given. The critical points. Now, generally speaking, we say critical points are where a derivative is 0 or undefined. Think more generally. Derivatives are rates of change equal to 0 or undefined. This really has a net rate of change. What are the two things that go into the rate at which the weasel population is changing? In and out. So this is when in minus out, the overall rate of change is 0 or undefined. Or you could say when in equals out. That's the critical point. Where are they equal? Because that's where you're going to hand off from increasing to decreasing or vice versa. So that's where you find that intersection point. I called it A up here. You actually need to find it, obviously. Anybody have that for me?
The point.
Yeah, the intersection time. 3.189? 19? Okay, thank you. Okay, cool. Now, how do I find, now I would normally then say, all right, I need to find the number of weasels at any given time. I have rates of change. How do I find amounts given rates of change? Integrate, yeah. I need to take the start plus the change. What's the starting amount of weasels? 400. And how do I find the change in the weasels? Integrate 0 to whatever time of, what do I integrate? What's the net rate? Phi minus r of dx or du or some kind of dummy variable. Okay, so t goes in later. All right. So I need to find n at 0, which is kind of a no-brainer. I know n at 0 is 400. I need to find n at 3.119. Darn it. And n at 8. That should get you started. Can you give this to me by the end of the day, or no, it's not happening? Are you being weasels? Somebody is just good sauce too. Can you turn this in by the end of the day?
I have some work
Now you, oh yeah, now you don't want to screw over your butt. I'll take it tomorrow at the start of the day. If you have a lot of questions, turn it in. Or, no, sorry. If you have a lot of questions, need help. Not what I meant to say, sorry. Yes.
Will you do this pencil veil?
Yes.
Yeah, I didn't have done
I thought I said, turn it in, you can stick them.
Yeah,
That's what you said.
yeah.
That was when you were gonna go over it. Oh. All right, I will not mark it late then, just turn it in. Okay. What? Oh, I thought you were talking to me.
I can. Done a bit. It's just like super weird for me. I've never done a bit. You know what? I worked hard.
That's spirit. Darn it, this is not. I should document. Hmm. Ah, boy.
Really, bro?
Yes. Oh. Oh, he had a pass. All right, would you do number 4 as a warm up, please? 4. Do number 4 as a warm-up.
Yeah, it was nice.